Ladies and gentlemen, it's about 52 years ago since Vinzenz and I met the first time. He, as a student in a high school in Switzerland, me as a young teacher for mathematics and physics in that school, and the class, the grade that he was in, had 6 students. And 4 of them were brilliant. And he was one of them. And it was quite interesting that he didn't learn. He always tried to understand, which is quite different to most of the students, because most of the students learn. But he didn't learn, he tried to understand. After finishing high school, he studied physics in Basel and did a PhD in biophysics, and went then for 2 postdoctoral fellowships, one in Oxford, where he was in a group with Rada, and one in Stanford, where he had the possibility to meet with Linus Pauling, the double Nobel Prize winner. That was part of his education in Stanford. After Stanford, he went to Switzerland, to Bern, the Coherence Institute, and was there for a while. And about 20 years ago, he was able to secure a grant from the Swiss National Foundation to come to Calgary and study dowsing. Dowsing. You know, that's when you go around and you look for water. There's a seat free here. And while he did that, he realized that the methods that we use in electromyography are archaic. I mean, we had measurements, we had electrodes on the skin, and we measured the muscle is on and the muscle is off. And he realized that there's much more information in that signal, that EMG signal, than people know about. So his whole development made a turn, and instead of being concentrated on dowsing, he started to concentrate on quantifying muscle activity. Today, it's not exaggerated to say that Vinzenz is one of the leading people in the world in measuring, quantifying muscle activity. And that was only about 20 years ago when he came. So the moral of the story is, in 20 years you can be world class. You. If you do it right. So why don't you listen to Vinzenz how to do it right when he talks today about EMG and what you can do with these signals. Vinzenz.
Thank you very much. Is it working? Okay. This is a picture of my dog, my favorite dog, Cicero. And as you can see, this is my life in Bry Creek, in the forest, in the wilderness, and we had a great time together. And so he was a very playful dog. What you can see on this dog is he is very musculous. And when you look at it, it's really something that we have to understand how these muscles work, whether it's in an animal or in a human being, or wherever we encounter it. And we have to know that when I arrived here, I would say 95% of all the studies were done with isometric contractions. So a contraction without the movement. Now tell me, what's the interest without the movement? Most of us do move. And especially we are in the human performance lab, and so movement is an essential part. So we got to adapt the technology for movements. Where is the thing to switch? Right, left?
Yeah.
Okay, so coming from looking at the sports activities that have been usual in the human performance laboratory, I had to have some new beliefs. And the new belief is in fact that muscles are very precisely controlled to perform these movements. And this, of course, is in contrast to what we had previously, where during an isometric contraction it was not so important when the motor unit arrived. And so lots of models were that these motor units arrived randomly and just superimposed. Now that's for sure not the case when you have physical activity. And so the actual timing when the muscle is active becomes very, very relevant during a dynamic task. Today I would like to talk about these two muscles, the vastus medialis and the vastus lateralis. These muscles develop a force across the kneecap, across the patella, when they get activated. The activation creates an electric signal. And this electric signal can be taken by two electrodes that are sticking to the surface of the skin. This electric signal is then amplified with an EMG amplifier. We have two different technologies. The classical technology, we amplified the potential. In this study that I'm talking today, the amplifier measures the electric current from these electrodes. So in fact, in a muscle, usually you have ions that activate the muscle. And so why should we measure the potential if we can measure the current? From this amplifier, you get an EMG signal, just the voltage output of the amplifier over time. We did a running study, and Martin Ulrich was here in this year. And in fact, he made a study on treadmill running for 12 males. And these 12 males, they ran at about 3 meters per second for 15 minutes. Now, 15 minutes were necessary to gather about 1,000 steps. So the analysis just with 2 or 3 steps, as is usually done, is not sufficient. You really need a sufficient amount of data. The electrodes were bipolar silver-silver chloride electrodes. And as I said before, the amplifier was a bipolar current amplifier. This amplifier has been built by Martin Ulrich and Daniel Comanduran with my help and with Kartik's help over in electronics. And so for the first time, we had a bipolar current amplifier working for EMGs. The signal that we use is 120 milliseconds prior to when the foot hits the ground. So this is foot contact. So either it's heel strike, or for a forefoot runner, it's the forefoot contact. So what are the questions that we really want to address? So how are the vasti muscles, these two muscles, in fact controlled by the motor unit at the motor unit level. And for this, we have a technology that is called coherence analysis that I will use today and present today. So one of the key questions, if we think about the dynamic movement, is how to analyze the short-term EMGs. And for that purpose, I have developed 20 years ago in Calgary the wavelet analysis, and so I will talk something about the wavelet analysis and show how this works. So now in running, of course, we have multiple steps, and each step is controlled by neuromotor control. But we have to balance, we have to adapt the steps. So we have a certain variability, and this signal also happens with different motor units. And so we have to ask the question is, what happens with the different motor units? Can we look at certain frequency bands, and would these frequency bands tell us something about the physiology behind the effect of these frequency bands? So having these 1,000 steps, we are interested in studying the variability of these steps. And then I have a very key question, and I would say that is the main question that at the end of the day I would like to resolve. Is now the central nervous system adapting every step for the condition we have right now at hand? Or do we have a kind of adaptation that uses a library of patterns, and we just pick out the pattern that is right? So in other words, we would like to see, is there such a library, or can there be clusters of pattern, and for that we will use a cluster analysis. Let's first see what happens in the coherence analysis. So we want to learn something about the synchronization of these two muscles. So we have the EMG from the vastus lateralis, the EMG from the vastus medialis, and this we have it for 1,000 steps, and for each step we make the Fourier transform for both muscles. For one frequency we can compute the coherence. So the equation for coherence, it's the cross spectrum, the norm of it squared, divided by the autospectrum of the two muscles. Now that is a bit abstract. So with the Fourier transform, we in fact take one sine wave out, and we can reconstruct these signals from multiple sine waves of different frequencies. If we look at one single sine wave, then in fact the sine wave looks like this. The red and the blue one represents the two muscles. If we plot them one against the other, we obtain a line. And this line is well known, correlation is 1. Now, when the things are shifted in phase, this is not anymore a line, but it becomes a circle. But we realize that this circle still means that the two signals are related to one another. And so the relation that we use is coherence. So the coherence is nothing else as then the correlation if we would adapt this phase to be perfectly superimposed. So coherence is the correlation without having to account for the phase shift of the signals. This is now the first result that we have for coherence analysis. We have the 1,110 steps. And for a coherence analysis, you need multiple steps to form this average. What we observe here is the coherence. We have realized the maximum would be 1. So we have a very high coherence that we observe here. And we can see that the coherence has a maximum at around 40 Hertz. Then we continue to higher frequencies, and we see that there is a second maximum that is at around 200 Hertz. And now we make a coherence analysis but not between the step and now the muscle activity, but the consecutive step. So one signal from the step now compared to the next step. And if we do that, our coherence completely disappears. So in other words, we are not repeating the same EMG signal from step to the next step, but within the step, the muscles are highly synchronized. And this synchronization happens with the raw EMG signal and is therefore a synchronization of the individual motor units. Now the big question is, why do we have two peaks? So is that the shape of the motor unit that has high frequency components and low frequency components? Or are there two different processes going on in this case? The consequence of this finding that we have this high coherence means in fact that we have a central control, and then we have the control of the motor nerve, and because the signal is coherent, in fact these two nerves must be activated at the same time. So we learned the first thing, that in fact we have a central command activating both muscles, motor units in both muscles in synchrony. Now when we look at the signal, we have a next question. And the next question is in fact, what is the amplitude or the power in such a signal? And we can see that the power starts very low, then increases and then decreases. So in fact, we don't have a constant amplitude that we have usually in isometric contractions. So it's very important to find what is the amplitude at a certain moment in time of this signal. The next question is, this signal has fast wiggles and then it has slow wiggles. So it has different frequencies. So where are these different frequencies coming from? And so we need a frequency analysis. And we want to know whether there exists kind of frequency bands that are typical for a movement. We would like to know whether these frequency bands correspond to certain fiber types, for instance, fast conducting fibers, slow conducting fibers, or what is the reason for this. And one of the things that was calculated in this laboratory was in fact the clustering of motor unit action potentials, and these clustering effects also cause frequency changes that can be explained. So how do we analyze this signal? For that purpose, I developed the wavelet transform very early on when I was here. The wavelet transform starts from a single wavelet, and then we use a scaling method that we get wavelets of higher frequency. What's completely new in this study is that the wavelets are non-linearly scaled. So we start with a Mexican hat, but we end up with an oscillating signal. And so in all classical wavelet transform, you have a linear scaling, and I developed for the first time a nonlinear scaling. The nonlinear scaling has the advantage that in fact the time resolution becomes physiologically relevant, whereas the time resolution in classical wavelets would be far too great for the high frequencies. Now, when we measure the length of a table or the length of something, we take a ruler and we measure with a ruler the length. If we measure the frequency, we need a ruler for frequency. So in fact, the wavelet is a ruler for frequency. We take the wavelet, we place it under the curve, under the measured EMG, and we slide it along. At every time point, we form the product between our signal and the wavelet. If the two signals are similar, then we get a high value. If they are dissimilar, we get a low value. And so now, in a color-coded way, we put here the magnitude we obtain by this multiplication. So we obtain a signal for different frequencies depending which of the wavelets we have used for this measuring of frequency in our signal. The process mathematically is called a simple convolution. So that's what we do mathematically. This is a slide that's from work that I have done with Maurice Moore. And here you see two EMG signals, again, from the VASTI muscles, from these muscles that I have shown at the beginning. And this was while walking. And so the thing was, if this signal is so coherent, if the motor units of the two muscles are practically arriving at the same time, why should the patterns be different? And if you look at it, you see that obviously these patterns are very similar. But they are not completely similar to the next step. So some similarity is between the step and the next step, but in general there are certain steps where this similarity is very typical. And that leads to the thing that originally we thought these patterns are more or less random patterns. But because they are so similar, they cannot be random. So in other words, there must be really an important structure and information in these patterns. Now, when you go to running, of course, the movement is much more stable and has a much lower dimensionality than in walking. And so we used the running study to further explore this similarity. So the hypothesis that we wanted to test is whether the patterns of the vastus medialis and vastus lateralis are more similar for one step than they are for consecutive steps. The second thing we wanted to test, and the second hypothesis, is that the EMG in fact creates distinct frequency bands. Normally, in the past, we have always looked at the global spectrum of an EMG. And these global spectrums, in my view, were just simply averaged out and had no real structure. So we have to look at these frequency bands, and I think that there will be frequency bands that reflect specific physiological events. And so, as I said in the previous slide, these patterns repeat from groups, and they form this library of patterns, and I believe we have such a library in our system. Now, we take the 1,000 steps, and we average the wavelet pattern of the 1,000 steps, and we get the first glimpse of it. Here we have all 12 subjects. For the vastus lateralis, the patterns. On the vertical axis, we have the frequency. On the horizontal axis, the time. 0 indicates our heel contact. As we can already see here, we have the two white lines that I put in just to help to see where the frequencies are located. So in fact, we have an activity above 65 Hertz, and this is repeated, but we have certain subjects, certain persons who really work with the high frequency component only. But in contrast, we have people who work with the low frequencies, with frequencies below 25 Hertz. So in fact, depending on who is running, they use different frequency bands when activating their muscles. Furthermore, we see that these people have only one band, but there exist people who in fact have duplets. So their muscle gets activated twice during a running movement. The next thing that we see on the average is in fact that these extend to lower frequencies. They are always extended to the right. So something happens not at the same time. Something happens later on. So now we have to analyze these 1,000 steps in more detail, and to that purpose we made a principal component analysis. So a principal component analysis now yields patterns that are called principal patterns. So you see here the first principal pattern, the second principal pattern, third, fourth, and fifth. And if you want to reconstruct the pattern that you had originally measured, you will have a contributing weight. So you multiply this pattern by the contributing weight, and you add it to this pattern multiplied by its contributing weight, and so on for all the patterns that follow. Now, when you have the signal, you can have a mean signal of all of this, what I have shown before in the first slide. To reconstruct the mean signal, you cannot do it with the principal component patterns. There will remain something that is unexplained by the principal components. And that unexplained part is called the residual. So we have to add to all the principal patterns a residual pattern to be able to reconstruct the full signal. Now, let's first concentrate on the first principal component. What we see here is in fact that we have at 65 Hertz a first activation, but then we have a high frequency activation up here. And we can see in the higher order patterns that now frequency bands start to form. Very distinct frequency bands. And the interpretation of such a pattern is this. If the weight of this pattern is great, then it means the higher frequencies will be more pronounced in the spectrum, and this frequency will be less pronounced in the spectrum. So in other words, that models the whole pattern of the spectrum that you will record. And the surprising thing is that this thing is in distinct bands. Now during that walk, the bands are not always like here, nicely superimposed at the same time, but they are dislocated in time. So in other words, we change the activity while we are walking. Now let's focus on the residual once more, and this line is foot contact. And if you look carefully, you can see that is yellow, blue, yellow, blue, yellow, blue, yellow, blue. This is a periodic pattern. And this periodic pattern obviously is common to all the steps. And we have made an analysis of this pattern with Christian Maurer at the time, where we can in fact see this periodicity occurring. The occurrence is dependent on the running speed. So as you run faster, it becomes more apparent. Now what is this frequency meaning? It's known as a Piper rhythm. Piper, that was early last century. And this is more or less a timing from the brain where the muscle adapts while it's active. So you have a muscle onset, and then for each of these periods, you can modulate the activity of the muscle. And that's what is used by the brain as a feedback loop to in fact adjust the muscle while it's active. And that's in a very short time. If you think about it, this is only a few hundred milliseconds. Coming back to our principal component analysis and the principal patterns, we see here an event where in fact the low frequency is absolutely separated from the mid-frequency band. So that cannot be one motor unit that is activated throughout, once giving a low frequency, then giving a mid-frequency. Something must be different. From all the measurements that we made, we can isolate these frequency bands. And as I have shown with the principal component analysis, is we have a high frequency band that is located in the range of 107 to 250 Hertz. We have seen there is a mid-frequency band that is in the range of 65 to 94 Hertz. And this mid-frequency band, in fact, is the band that we would obtain if you take a random superposition of motor units that are published in the literature. So this is the main band that you would expect. And this band, of course, will react to fatigue. So when the propagation of the muscle activity gets slowed down, the conduction velocity of the muscle gets down, then in fact the classical fatigue will reduce that frequency band. If we look at the 40 Hertz band, and I remember this 40 Hertz band was the band where we had the maximum in the coherence analysis. It's between 34 Hertz and 53 Hertz. And this, in fact, is the clustering effect of motor units. So if you have a single event of a muscle, your motor units cannot be spread. They must come at one time. And so depending whether this is a bit broader or a bit more narrow, they will really cluster. And these clusters then, for model computation, will reduce the frequency to the 40 Hertz band. And then we have seen before, we have the low frequency band, 25 Hertz and below. And really what happens there, we don't know. One explanation for the low frequency band would that it's caused by duplets or kind of duplets. So duplets is the muscle get activated and the action potential just induces a second activation. Where the kind of duplets, you have an activation from the neuron and a second pulse from the neuron activates the next pulse, but very, very close together. And these would broaden the motor unit action potential and therefore they would reduce it. Now, these duplets occur normally at the beginning and at the end of the muscle activation. That's why we expect that these things are visible in our patterns later on or early on. Now we had these principal components or these principal patterns. And I said we have a contributing weight for each one of the patterns. So here we show now the weight for each one of these principal patterns. So the first weight is all positive, but these weights, they scatter. We can see that these weights are pretty steady throughout these 1,000 steps. So in other words, these patterns are used on a regular basis, but they have a statistical distribution. Now, in fact, we can generate new patterns that are artificial patterns. We just take the same distribution, the same weights here, and we just generate thousands of new patterns that are just called surrogate patterns, artificial ones. We see that the residual pattern has a slight positive value, but in fact, compared to the other patterns, has very little scatter. It's something that is common to all these steps. So the piperism is common to all these steps. Let's go back to our similarity. Now we need a measure for similarity between the patterns. And at hand is a simple correlation of such normalized patterns. Now, in fact, correlation is not an ideal measure for us. So we used 1 minus correlation, which we call dissimilarity. Now, why use a dissimilarity? You all have heard as clustering analysis or nearest neighbor analysis, where in fact we look for objects that have the smallest distance between them. So instead of asking for the smallest distance, we ask for the smallest dissimilarity. So we use that as a measure, in fact, to cluster these patterns in those that are similar. Similar patterns have a very low dissimilarity. So we use a hierarchical cluster analysis and do such a cluster analysis, and the result is shown here. We have the vastus lateralis, and each color represents a cluster of steps, And so you have broader clusters with multiple steps, and you have clusters that have only very few steps in it. But these clusters are just forming a limit of 20% dissimilarity, and if you allow a higher dissimilarity at one point, they are all included. So everything that is in color is now below a threshold that we use to find these clusters. We find these clusters for the vastus lateralis and for the vastus medialis. Now we take these surrogate patterns that I was talking about before, and we do the same cluster analysis with the surrogate pattern, and we ask, are these random patterns, can they also form clusters? And indeed, they form clusters. The difference is very subtle. You see that you have still big clusters, but most of them are smaller. So now we need to know something about the distribution of these clusters. So we do a histogram of these clusters and see what the histogram look like. So the histogram of the cluster tells us if we have 40 steps in the cluster, then we have only one cluster. If we have a number here, let's say 10, then we have 4 clusters with 10 steps in it. And so we can calculate a median of this curve to say where are the number the same on both sides of the median. We do the same analysis with the surrogates. And in the surrogates we see that they are all pushed to smaller steps in the cluster. So the cluster size is much smaller in the random than it is in the real world. And that, in fact, you see for the vastus medialis exactly as you see it for the vastus lateralis. And that is, in fact, the proof that these patterns are not just random for every step, but that you have maybe cluster in the 10th step is the same then in the 100th step, is the same then in the 160th step, but these clusters nevertheless are similar. So now we ask ourselves, what are the results that we have now? So we have seen that the cluster size, the median size, is about 19 for the vastus medialis, about 17 for the vastus lateralis, so an average about 18. And in the surrogates, these fall down to about 7, and with a standard deviation of about 2 to 3, we can see that this is highly significant. So clusters are not random clusters. And then we have seen that the correlation between the patterns is relatively high, but if we make a paired analysis between the correlation and the correlation for a consecutive step, we see that we get a positive value, and that value is highly significant as well. So in fact, it is true that the vastus lateralis and vastus medialis pattern is more similar within a step than between consecutive steps. Now, let's look at these clusters. And I selected from these clusters that are larger than the median value, those two that were most dissimilar. So in fact, we have a huge dissimilarity between these two curves. And we see that, in fact, in this cluster, all the activation happens at high frequency and later on at the low frequency. During the same run in the other cluster, we can see that the activity was at the low, but the high frequency activity is gone. So in fact, there are steps while running where the high frequencies do not occur. We see here these two patterns, and we see clearly that is the mid-frequency band, 65 Hertz to 94. This is the 25 Hertz band, and the 40 Hertz band is not active. Whereas in the other cluster, the 40 Hertz band is active, and this one is not active, and we have a little activity below 25 Hertz. So that means that really these clusters are separated by the frequency bands, so by the physiological effect that cause one or the other band. We can look at the same thing in another subject, and then when we look here, for instance, we see all the three bands. The 40 Hertz band is missing, and the 40 Hertz band is in the other cluster. So now we can in fact select these frequency bands and can integrate the intensity of these frequency bands and see how the intensity varies while we are running. And so we can see that the low frequency, for instance, increases its intensity from 60 to about 70. We can see that there is a huge variability for the individual steps, but if we smoothen this, we form an average. This average shows a trend. And we can see that the trend here is upwards, whereas in this band, the trend is horizontal. In the mid-frequency band, we see a slight modulation. In the high-frequency band, we see a stepwise increase and clear modulation of how these things are used. Now, if we assign a separate motor unit, a separate type of motor unit, to the high-frequency band, we can say we observe the high-frequency band here, and so we are not always using the same number of fast fibers that we use during the run. Now we can look at a specific area in here, and that specific area shows a kind of a dip here with a peak. If we look here, this gets to a maximum and the peak is not there. So in other words, these mean values are not correlated. And I'm currently in the process of evaluating the correlation between these curves in higher detail to see, but the first thing is these frequency bands are activated individually. We see that in another subject, but the last subject that I would like to show here is now a typical subject that was not running in a steady state form. And here we see clearly that the low frequency band is not occasionally derailing, but in fact it has a trend. So we can see how these fast fiber types are now used and how gradually we use more and more of the fast fiber types. Whereas the mid-frequency band here remains absolutely stable. So my conclusions here is that the motor units are highly correlated between the vastus medialis and the vastus lateralis. The patterns of the VM, VL of one step are more correlated than between consecutive steps. So it's very important to see this. And then we have seen that these patterns are not random. They have distinct structures. So these distinct structures, they allow, in fact, to form these predefined patterns, to find these predefined patterns. And what really characterizes the predefined pattern is the different spectral bands, the different ways these frequencies were generated. With that, I would like to thank you for your attention. And you have seen before my dog running. This period of running of a dog is over. And now I'm returning in the region of Basel, where I will enjoy the Fasnacht and will enjoy things that are over there. And so the life will change, and this band will now coach me over to my new situation in life. Thank you very much.
Thank you very much for your talk, Doctor. As you know, I'm not an non-academic, but something that intrigued me was the issue with the brain. Now, are the two muscles that you investigated, are they talking to one another, or do they transmit to the brain and the brain dictates to those two muscles?
No, the brain on first hand gives the command to the muscle, and it gives it at the same time to both muscles. So they are not talking with each other, but they are stimulated from top to the bottom.
I have a further question. If a person suffers a stroke and then they lose that muscle function, and you have brain plasticity, and another region of the brain becomes initiated, what do you think will happen to those clusters?
Well,
I know it's speculation.
It's speculation if you, and especially it's a wide speculation if you go to a stroke. But we don't know exactly the point where this common activation happens. It can be spinal or it can be from the brain. So if it's spinal, it will remain. If it's from the brain, it will be disrupted. Now, I think that this is a new tool that we can use very much in biomechanics. And for instance, if you have an injury, you don't need to have such a hard injury like a stroke. But if you have, for instance, a torn ankle joint, you lose proprioceptors. And as you lose proprioceptors, something is missing to compute the pattern of the new, to compute the pattern of the next step. So what we expect, and one of the studies of Maurice Moore will now see with osteoarthritis, whether during osteoarthritis, which typically occurs after an injury, 15 years later you have osteoarthritis, might well be that the coordination of the two muscles get out of synchrony, and then you have lateral shear forces, and these lateral shear forces cause inflammation. So one of the hypotheses he is now testing in his PhD thesis is whether really these two muscles get out of coordination.
Thank you.
What do you think determines a cluster? So certain steps happen to be less dissimilar than others, and they form a cluster, but where do those steps come from? Is there a clear relationship to, say, in time or the number of steps? Like, why do they belong to the same family, and why are they selected when they're selected?
Well, that leads also to further research, but I can tell you that we already have certain results, but they are not as clean as I would like them to present them now. In fact, you have seen that these patterns, these, let's go back to the slide.
It's right here.
Thank you. Here you have this high variability, in fact, in certain frequency bands. And so one possibility is that this repetition is in fact random. So a first guess would be that your stability needs randomly, depending on how you stand, how you run, what you do. So this is random. Now, as you know from previous talks that I had, in fact, this randomness can be tested by entropy measurements. And we clearly see that the entropy changes. So in fact, there is structure in this random signal. But this will be the next research project.
The take-home message that I got from your presentation was that we have similar kind of pattern between VL and VM. However, yes, we have different patterns between steps.
Yeah.
And during your presentation, you mentioned that one of the contributing factors in these changing patterns are reflexes. are the reflexes, right? The reflexive mechanism that change
Yes.
the pattern, right? The reflexive mechanism needs at least 100 to 200 milliseconds to adjust the movement. But if the frequency band changes within each pattern, it doesn't have that much time. Like each step is going to be sometime done in less than 200 milliseconds, and you do not have enough time to adjust it. So how come the frequency band changes from within steps?
So I think you misunderstood some aspect of it. I didn't talk about reflexes. So reflexes for sure would not have the necessary time to do it. So in other words, the proprioceptor information is collected as a whole. Once it's collected, it generates the pattern for the next step. But that includes your visual input, the sensory input, and all of it. So we have a kind of, well, that's my view, we have a kind of pre-activate, so a predefined activation based on the past. And there we have enough time. The piperism is another story. The piperism is about 30 milliseconds. And that must be guided from somewhere else. But this is a modulation. And whether that involves this kind of a feedback, I don't know. I don't know yet. We just simply see it, and we see how it modulates the activity of the muscle while it's active. So it seems to be a correction mechanism, but it's most likely not a reflex, because, as you said, it's too rapid. It's about 30 milliseconds.
Can I just make a quick comment to that? Because reflex responses are faster than 200 milliseconds.
Some, yes.
When you do an EH reflex response, a spindle reflex response, which will be a typical response in a muscle. You talk about the muscles here, then they are well within 100 milliseconds. I think what you might mean is it might be taking a long time because the force is really slow to react. When the activation changes, then it takes another 80 or 100 milliseconds. So the reflex response is 80 milliseconds, and then the force is another 80 milliseconds. That gives you, 200 milliseconds. It's relatively late. But you're not measuring force. You're measuring activation. And activation changes should easily be visible within the 300 milliseconds that you measure.
That's possible, yes. And I had this at the beginning of the talk because I expected your question. So
I didn't even want to bring it up. I just want to clarify.
So the electromechanical delay, in fact, is an issue in here. So really your force is about 30 to 80 milliseconds later than what you see on the EMG. Now, one of the possibilities is to say we have an electromechanical delay that is different for different fiber types. So in other words, the delay that we see might be an adjustment in such a way that the force arrives at the right time. We have not measured this, but in my simplicity of the analysis, I said if we assume that the electromechanical delay is always the same,
which it is not.
Which it is not. Then we would say the EMG activation pattern is similar to the force activation pattern, but that's most likely not the case. So for the time being, we are limited to what we can see, and that is the EMG. And these patterns have these similarities, and I would still say that if two patterns are similar, then they will generate a similar force pattern. And I think that's a absolute decent statement.
Sorry, I would like not to contradict what you mentioned for sure, or confront what you mentioned. The only thing is that you mentioned it's not a reflexive mechanism, but if I'm not mistaken, it is a reflexive mechanism because first of all, it's not voluntary. So when it's not voluntary, like when these guys are running during those 1,000 steps, they didn't think about it when they were running.
No.
And most of the time, we do not think about our running steps or walking steps when we do it. So it's a reflexive mechanism because it's non-voluntary. And the second reason is that, as you know better than me, it's controlled at the level of central pattern generator, and central pattern generator is only actually controlled with reflexive mechanism unless you voluntarily change your pace from slow to fastest, or from, for example, from walking to running. So I'm still confused, but I'm going to talk to you about that later.
So let's just answer this in a simple way and very superficially. Most of our activity is subconscious, and only about 10% is conscious. And nobody would change his gait pattern consciously in normal everyday life. So when you're absolutely correct. When you are running, you are not doing anything consciously. However, to say that therefore the brain is not involved might not be the right conclusion. Your subconscious might control it. So your sensory input is not processed in the conscious part of the brain, but in the subconscious part of the brain. And in fact, your next step is programmed. And then the command is going down the line.
May I just add, and I think we have to be very careful about pattern generators, because in some animals they are very pronounced. And as far as I know, in human animals, they are not so pronounced. And without the brain, we are fairly useless, and stepping patterns are very hard to initiate, whereas in cats or in other animals, without the brain, under the right external conditions, you can evolve relatively easily kind of a regular step-by-step walking pattern. But as far as I know, that's really not true. I don't think we rely very much on pattern generators like some other animals do.
No, we rely more on this agglomeration and preparing a next pattern in our brain. And that's exactly what happens. If you decerebrate the cat will still walk. So for walking, you don't need the brain. But if you look at how they walk, and that's again something I learned from Walter, is if you look at how they walk, this walk is not stable. This becomes very erratic. So in fact, the brain is needed, even in animals, but even more in humans.
One of the surprising results is that when you have the step-to-step comparison, that correlation is much smaller than the between one step.
Yeah.
Did you expect that? And I didn't expect that. Why is that the case? You know, if you see a person running, you think they do the same thing the whole time.
Yes, but we only see an overall pattern of the movement.
Yeah, but did you expect that result?
More or less, yes, because we went in that direction to look for it, because we hypothesized that something must change from step to step to keep the stability. So these must be minute changes. So overall, these patterns had 0.77 correlation. So the overall correlation was still very high. So these patterns are all similar because we are running. It's the basic running movement. But nevertheless, now if we have a correlation between a 70% correlation or 70.5 correlation, this makes the difference for your stability.
Sorry for continuously adding things, but about 20 years ago, with Vladimir Zatsiorski, or 25 years ago, we did this study where we had exactly like you, dozens and dozens of step cycles in the cat hind limb, and we measured medial-gastric, lateral-gastric, and Taris and Soleus forces that contributed to ankle extension. And the very surprising thing was when we had these cats walk and run, the total ankle torque was virtually unchanged, but the individual muscle forces, how they contributed, changed dramatically, sometimes by 30, 40, 50% from one step to the next. That all was fascinating. It's exactly what you said. The basic movement is maintained, but internally there seem to be all kinds of strange and varying things going on. So at the end of the day, you get the right ankle movement, with completely different combinations of the individual muscle forces. And that always fascinated me.
Yes, and I think that's a general trend that we observe, and that leads to Benno's statement: we have a preferred movement, and to maintain a preferred movement, the muscle must adapt. But on the other hand, even a small intervention, another shoe or something like this, will change the kinematic, but maybe so little that you don't observe it just by looking at it. So the general thing is that really the movement remains the same, but to keep the movement the same, you need to control it.
I'm going to ask a complete layperson here. How does fatigue factor into this? If you run your test to failure, does the brain keep sending the same signal and there's just no response at the end? Or is the signal changed too?
So in the classical EMG analysis, everyone talks about fatigue. So fatigue is kind of one of the general topic in EMG. And what people talk about fatigue is usually what's called peripheral fatigue. So it's not how the brain controls the muscle, but how the muscle in itself suddenly is unable to produce the force. So we have a peripheral fatigue. And the peripheral fatigue, in fact, results that the propagation in the muscle of your signal is slowed down. So this is observed as a reduction in frequency. Now that's exactly what I want to come to in future studies. So the studies that we did here, we had people doing 600 squats, 600 times up and down. And then you have fatigue. And then you can in fact see how the coherence now decays. So in other words, our brain is then not able to maintain the correlation between the two muscles. And if you look at the weightlifter and he goes to the extreme, you see that initially he is able to smoothly go up. Later on his legs will shake. So he will not be able to coordinate the muscles anymore if he's fatigued. So this would be central fatigue. And now with this tool, we can address central fatigue.
I think your work on the clustering is fascinating. But I wanted to get your insights on the amount of clusters that you...
Of the amount of?
The number of clusters that you found in your hierarchical clustering. And if it makes sense to you that there might be that many patterns at work. So does it make sense to have that size of library that you take advantage of?
We have to be very careful. And I would say that is a first indication in this direction. We have nothing of the kind up to now. And so we don't know how this changes. It also depends very much of where I put the threshold, whether I get more or less clusters. So threshold was based on the statistics of the system, so that for all my trials I had one standard deviation below the mean as a threshold. Now, that is as arbitrary as taking a constant value. So the interesting thing now will be, if you have a constant threshold or a defined threshold, will these clusters change with external conditions? So would we, for instance, have more clusters when walking than when running? What would be the differences? This is the first indication that we have, in fact, kind of common patterns. But whether that size today is perfectly accurate or not, I wouldn't put my hand in the fire for that one.
Nice talk, Vinzenz. I had a quick question to go back to the timing.
Louder, louder.
I had a quick question to go back to the timing of the EMG responses and the potential involvement of reflexes in driving the muscle activity. So in the arm, where the pathways are much shorter, if we see a 50% increase in EMG, we don't see differences in kinematics until about 180 milliseconds. The pathways from the leg to the brain are much longer. So to say, have you looked at careful that saying that the EMG within a single stride is being driven by corrective responses from the brain? In order to sort of get more at that question, I think it'd be interesting to actually distinguish people's gait cycles. So to have people walk have the the force sort of move under their foot and look at the latency of the EMG activity related to that disturbance. And I think that you'll find that it's much later than the latencies that you see here.
No, I think it's really a good thing that we look for new projects, and I think these kind of projects are important. And what I have done over these 20 years is, in fact, what I've shown you today is to give an analytical framework that allows now to address all these questions. In my time, I haven't had time to address all these questions. Especially, for instance, that question: how can it come that one frequency band representing one event can be completely independent from another one? These things are puzzling. These were not known 10 years ago. And so we have now the tool that we know that these different frequency bands cannot be looked at once, all of them, and just make a Fourier transform and a power spectrum. But these questions of latencies are now suddenly all possible. And that's what I would like to give to the next generation in this lab.
And you're probably aware of that, but work like that has been done. There's like shoes that in the step cycle all of a sudden flex your ankle joint. You kind of stretch the gastric muscles. In fact, Paul Lee here in Calgary and Dick Stein in Edmonton did that, roughly 30, 25 years ago when I arrived here. So there is some work.
There is work
exactly
done, yes.
that on
My
that.
understanding is that cortical drive when you bring the brain back to the muscle doesn't show up until after 100 milliseconds.
I don't know those results. This is not my field, but I know those studies have been done. They have been done here in Calgary and also in Edmonton. But I don't know how long it takes.
Why isn't there a peak of the coherence of the two muscles at the fundamental gate frequency?
At what? At the 40 hertz?
Say the step frequency.
Yes.
Why don't you see another peak of coherence?
I can't answer the question from the step, but I can answer the same question from the activation of a motor unit. The activation of a motor unit has a fixed repetition rate, like a step rate. And if you look at the power spectrum, then you see that in fact the repetition rate is barely visible in the power spectrum. So these two things are really separated. And I assume it's the same thing in the gate, but I would have to do the model computation.
Okay.
All right, thanks a bit. Speaker. He will be the director of HBL, Dr. Walter Herzog. He will deliver a Malbridge Award lecture. It's called Reflection on Muscle, Truth, Serendipity, and Paradigms. So please come back next week. Now,
First, an announcement. After, in about 5 minutes, we have some drinks and some munches out in the atrium. You are invited to join us. The Dean sponsors that. And I would like to thank Vinzenz for everything he did. And everything he did is in this book. In the last 20 years, he had more than 50 publications. And we have printed those publications, all of them. And want to give them to him, but he has them already. But what we also did, we asked the students, it's too heavy. We asked his students and co-workers to write something to him. And that is in that book too. And I would suggest to you to read some of those statements. It's fantastic. The lives that he has touched, the people that he has helped. You know, you that are from the Human Performance Lab, you know that he sits out in these chairs and he talks to people for hours and explains the things and brings these people up and up and up and up to the highest possible level. It's unbelievable that what you have contributed to the lab, and I would like, in the name of the Human Performance Lab, thank you for all that, for your scientific contribution, but also for your human contribution. Thank you very, very much.
Thank you very much. Thank you very much. I would like to thank all of
I didn't tell you, that's my But I didn't tell you. Vinzenz 5 was in the same school as Vinzenz. And Vinzenz had a dispense from all the sports but skiing. Can you imagine a doctor gave him dispense that he doesn't have to go to all the sports, but skiing he can do. And Michaela was living in the village where this boarding school was, in a house. And after skiing, Vinzenz would always, instead of going back to the school, going down to Michaela. So I would like to thank you for the support that you gave Vinzenz over all that time.
So in my turn, I would like to thank that I was allowed to be here and in fact had the freedom to do all this research, because lots of it people wouldn't have believed when I started it. And so I was very happy that I had the support of the Human Performance Lab, of Benno, and especially that all the students were interested in what I'm doing. That was always fun for me to transfer and discuss these things, and then I learn from the students. So thank you very much, all of you.